Good morning. Last time I had talked about how to solve for capacitor problems, and I had introduced a theorem that we call the uniqueness theorem. What the theorem says is that if I have any volume, call it V, if I have some known charges inside that volume, and if on the surface of V I know either the potential or the normal electric field, because del phi del n is minus E n at every point on S. So, if I know what charges are inside this volume and on the surface of this volume I know either at every point I know either phi or del phi del n, then the solution inside is unique, meaning there cannot be two solutions that satisfy this information. Now, as I said, the importance of this comes from looking at ordinary differential equations. If I were solving d squared x dt squared plus k squared x equals 0, that is like solving Poisson's equation. Well, I will get sines and cosines. It does not tell me the function x. The function x could be any combination of a sine and a cosine. Supposing I further knew that x is equal to 0 at t equals 0, that still does not determine what x is, because the general solution for x would be of the form a cos kt plus b sin kt. So, at t equals 0, x equals a, and I am told that at t equals 0, x is equal to 0. So, I know that a is 0. So, that tells me that x equals b sin kt. If I now know one more piece of information, let us say that x of pi over k is equal to, well, pi over k is bad, pi over 2k is equal to 1. Then I can substitute in here, I will get b sin k times pi over 2k, k cancels out, so that is b sin pi over 2, but sine of pi over 2 is 1, so this is nothing but b, and that is equal to unity. So, given both these pieces of information, I am now able to say x is equal to sin kt, which finally fixes x. So, it is only after I know both the differential equation and two pieces of information that I am able to solve and get the actual form of x. If I did not have this, then any function of this form, namely x equals sin kt, x equals minus 2 sin kt, all of them would have been solutions. So, when you try to propose a problem of solving Poisson's equation inside a volume, the question becomes, what additional information do I have to say besides saying del squared phi equals minus rho over epsilon. This is the equation itself, and this equation is exactly like specifying this equation. And just as this equation does not pin down x itself because you need additional information, similarly specifying this equation does not pin down phi. It pins down a lot of the details of phi, but some information is still remaining. Basically, if I could solve del squared phi equals 0 inside this volume V, then if I add these two, so if I call this phi 1 and I call this phi 2, any solution phi 2 that satisfies Laplace's equation can be added to this solution. So phi 1 plus phi 2 is always also a solution. So that is why this equation by itself does not give me a unique answer. So what this theorem is telling us is that to get a unique answer, that is to specify enough information, all I need to do is on the boundary, at every point on the boundary I specify either phi or I specify the normal component of phi. The proof of this is in your textbook and you can read it. I will leave it as a exercise because it is not very illuminating. What is more useful is to use it. I am going to use it in two ways in today's class. First, I am going to talk about the method of images, and secondly, I am going to actually use it to solve Poisson's equation. Let us go first for the method of images. You have a ground plane, it should be a straight line, imagine it is. This plane is kept at 0 voltage and I want to find the solution of phi for this problem. This problem is difficult because I do not know what charge is present on this plate. What I know is the potential. Therefore, I can't apply Coulomb's law. However, as I did last time, supposing you put a charge minus q and you put the charge minus q as far below this plate as the charge was above, then if you take any point on the plate, create the triangle, because these two distances are equal, clearly these two angles are equal. This charge attracts towards itself, so the electric field is pointed this way. This charge repels, so the electric field is pointed this direction. Both these angles are equal, that is, both are theta. So if you add these two vectors vectorially, you will get a net electric field that points straight down. Now, what is the advantage of that? So, we have got that the electric field at any point P is equal to q over 4 pi epsilon naught times 1 over, I am going to call this distance r squared plus d squared times the direction. The direction is, I can construct it out of these two components. So, it is equal to r hat plus minus d z hat divided by square root of r squared plus d squared. What I have done is, I have said that to construct this direction, I have to go d distance in the minus z direction and r distance in the r direction. So, minus d z hat plus r r hat, but that gives me a vector with length. So, I am going to divide by the length of the hypotenuse itself, which is square root of r square plus d square. So, the magnitude of this vector is 1 and its direction is the correct direction. This is the electric field due to this charge, and the electric field due to this charge is minus q over 4 pi epsilon naught 1 over r square plus d squared. Now, the vector direction is minus r r hat minus d z hat divided by square root of r square plus d square. So, I should, since I have taken the sign of the arrow into account, this is actually plus. So, now you can see what has happened. D is minus in both cases, so they are going to add up. R is plus r here and minus r here, so they are going to cancel. So, the net result is I get an answer which says the electric field is q over 4 pi epsilon naught 1 over, if I combine these, it is r squared plus d squared to the power of 3 halves, that is r squared plus d squared to the power of 1 multiplied by r squared plus d squared to the power of half. So, r squared plus d squared to the power of 3 halves, and then multiplied by 2d z hat. That is adding up this term and this term. So, as this figure shows, the electric field is in the minus z hat direction. Now, what does that mean? If the electric field is in the minus z hat direction, we can conclude something immediately. We have a point charge q, we had the ground plane, and we had our image charge minus q. Now, at every point on this ground plane, the electric field is in the z direction. This is the electric field. Now, far away, the potential goes to 0. That is because if you have point charges, our derivation from Coulomb's law tells us potential far away is 0. Now, the potential anywhere here, phi at any point z equals 0 r is equal to minus integral r to infinity E dot dl. That is by definition, that is how we define potential. Potential is negative of E dot dl. But E is in this direction and dl is in this direction. Therefore, E dot dl is identically 0. So, if I move along this ground plate, the electric field is always perpendicular to the way I move. So, this is identically 0. Let me, so when I write this as phi equals z equals 0 r, I really mean phi of z equals 0 r minus phi at infinity, but phi at infinity is 0. So, I have got that phi of z equals 0 r is always 0. So, what has that achieved? I started with this problem. I started with a problem that I wanted a charge and a plate which is kept at ground voltage. I want to know phi here. I took this problem and I replaced it with a new problem. I still have a charge q. This charge q is a distance d above the origin. I put a minus q charge here, which is a distance d below the origin, and I removed this ground plate. The ground plate is no longer there. So, I have only 2 charges left, and if I have only 2 charges whose locations I know, whose values I know, Coulomb's law gives me the answer. So, the electric field anywhere for any r and any z is going to be equal to, let me write it where there is space, the electric field anywhere at r z is going to be equal to q over 4 pi epsilon naught. This charge is sitting at r equals 0 d, this charge is sitting at r equals 0 minus d. So, the electric field is going to point away due to this charge and is going to point towards this charge, and it is going to be the vector sum which is going to be the actual electric field. It is a dipole. So, it is going to be the, I will just write it symbolically because otherwise it becomes messy, r minus r1 divided by r minus r1 cubed minus r minus r2 over mod r minus r2 cubed, where this is r1, this is r2 and this is r. I will leave it as an exercise for you to work out the actual values. It's actually quite easy, because r minus r1 is nothing but r hat plus z minus d z hat, and r minus r2 is nothing but r hat plus z plus d z hat. So, just substituting these, you can work out what this expression is. Now, what is important to understand is we have taken one problem where we had a charge and a conducting plate. We have solved a different problem where we have 2 charges. Now, both of them give you solutions. So, this problem gives me a solution, so does the other problem. The uniqueness theorem tells us that since I have the correct charge in the region above the z equals 0 point, because the solution with 2 charges gave me the correct potential here, this answer is exactly the same answer that I would have got if I had solved this problem of the plate and the charge. So, let me repeat. I will put down the steps we followed. Start with charge plus conducting plate. All right. Place image charge beneath plate. And remove plate. Solve Coulomb's equation law for charges. So, we do just this step. We start with the problem charge plus conducting plate. We replaced the plate by an image charge. Having replaced the plate by an image charge, we could use Coulomb's law and we get the electric field. The important point about this is we are solving a different problem. We are not solving the same problem at all. However, since both problems have same charges in z greater than 0, and since both problems or both solutions satisfy phi equals 0 at z equals 0, since both of these do these two things, that is, they have the same charges in z greater than 0, namely the original charge, and they both go to 0 at z equals 0, they are the same solution. It is a remarkable theorem actually, and it is a remarkable simplification you get because of this theorem. The method of images can be used in different geometries. It is a very specialized tool. Where you can use it, it simplifies a lot, but there are only a few geometries where actually you can use it. So, instead we go to a more general kind of technique which includes the method of images, but that technique also uses the same trick, and I am going to illustrate that technique by solving a problem we have already solved. Take a capacitor plate. We have the bottom plate grounded, top plate held at V naught, and we have epsilon 1 and epsilon 2, two dielectrics. This is x equals 0, x equals x naught, x equals d. We have solved this problem earlier by saying, let us take the displacement vector. Displacement vector does not see any charge except on the top and bottom plates. Then apply Gauss's law. You prove that displacement vector is constant. So, since displacement vector is constant, electric field E x is equal to some constant c divided by epsilon 1 in region x naught less than x less than d, and is c over epsilon 2 0 less than x less than x naught. And from this we can calculate the solution, and we have done that. Now, what I am going to do is I am going to do it slightly differently. I am going to go back to the original equation and try and solve it in two parts. So, in order to do that, for reference, let me write down what I get as the solution using this method. The potential phi is equal to E x in this region is E x times x, and it is equal to E x times x naught plus c over epsilon 1 x minus x naught. Where this E x is c over epsilon 2. So, let us see if we can recover this solution by another method. What I will do is the following. I have my parallel plate capacitor. So, x equals d, x equals x naught, x equals 0, and I am going to label this region as region 1 and this region as region 2. This region has dielectric epsilon 1, this region has dielectric epsilon 2. And I am going to say I am going to solve Laplace's equation, because I know that the electric field E x is equal to minus d phi dx I know that divergence of d, which is equal to d dx dx, is equal to 0. There is no charge, no real charge here. So, what that means is d dx of minus epsilon d phi dx is equal to 0. So, if epsilon is a constant, I can combine these, I can pull the epsilon out. So, I get d squared phi dx squared equals 0 if epsilon equals constant. But epsilon is constant in region 1 and it is constant in region 2. Where it is not constant is at the boundary between region 1 and region 2. So, let us solve this problem. D squared phi dx squared equals 0. The solution, I integrate both sides with respect to x, I get d phi dx is equal to some constant. Let me call it constant C1. I integrate again, I get phi equals C1x plus C2. So, phi is a straight line. So, now let us apply this to region 1. In region 1, phi is equal to C1x plus C2, but I do know that phi at the top, phi of x equals d is equal to V naught. That is part of the problem specification. It is V naught here and it is phi equals 0 at the bottom. So, if I substitute d in here, I should get V naught. V naught is equal to C1x, C1d plus C2. This allows me to connect up C1 and C2. For example, I can say C2 is equal to C1 is equal to V naught minus C1d. In region 2, phi is equal to say C3x plus C4. Now, again I have a piece of information which says phi of x equals 0 is equal to 0. Substituting x equals 0, C3 into 0 goes away. So, 0 equals C4. So, I have C4 equals 0. So, now what do I have? Let me summarize. I have in region 1, I have phi is equal to C1x plus V naught minus C1d. This is C2. And in region 2, I have phi is equal to C3 into x. Now, what I am going to do is I am going to connect up these two solutions, and this is where once again the uniqueness theorem comes. Now, you can see that this region 2, I have a solution for potential, but the solution has a free parameter. So, the solution is could be phi equals x, or phi equals minus 2x, or phi equals 5x. All of them are valid. That is because I do not have enough information to decide which coefficient is multiplying x. It is just an unknown coefficient. But actually the problem knows. The problem has been fully specified. It is just that in the part that I am looking at, I do not have enough information. what I will do is I will say, supposing I do know what the potential at x equals x naught is. If I knew that piece of information, then I can pin down C3. So, how can I get that value? Well, I can get that value from looking at region 1. Phi at x equals x naught according to region 1 is C1 times x naught plus V naught minus C1d, and according to region 2 it's equal to C3 times x naught. So, I have a connection between these two. In other words, I know that these two are both talking about the same potential. In this diagram, this piece is talking about the potential as I approach from above towards x equals x naught. This is talking about the same potential as I approach from below, but the potential should be the same, because potential is nothing but the work I did to get to there. Whether I got in this way or this way, we have already shown it does not change. Therefore, these two must be equal. So, it already gives us one equation. Now, there is another equation we have. The other equation is that if we make an imaginary cylinder which is very flat, so its sides are narrow, top and bottom are much broader, then the amount of flux entering must be equal to the amount of flux leaving, because there is no charge at the interface. I can work out the amount of flux entering and leaving. Actually, because of the way I have put it, it should be pointing upwards. So, d in region 1 is equal to minus epsilon 1 d phi dx. If I take the derivative of phi, I get it's equal to minus epsilon 1 times C1. D in region 2 is equal to minus epsilon 2 d phi dx, which is equal to minus epsilon 2 C3. So, I therefore have two equations. One equation says C1x naught plus V naught minus C1 d is equal to C3 x naught, and the second equation says epsilon 1 C1 equals epsilon 3 C3. This equation is what is called continuity of potential, and this is nothing but Gauss's law. I have two unknowns, C1 and C3, and I have two equations. I can solve them. By looking at this first equation, the second equation, let me write it out, epsilon 1 C1 equals epsilon 2 C3, it should be epsilon 2. So, that tells me what C3 is in terms of C1. So, I can write C3 is equal to epsilon 1 over epsilon 2 C1. Now, let me substitute into the second equation, into the other equation, C1 x naught plus V naught minus C1d is equal to C3 x naught. But I know what C3 is. It's equal to epsilon 1 over epsilon 2 C1 x naught. So now I have only one unknown and I have one equation. Let me combine the two. C1 x naught times 1 minus epsilon 1 over epsilon 2 is equal to minus C1d is equal to minus V naught. So I have taken C1 x naught minus epsilon 1 over epsilon 2 C1 x naught minus C1d is equal to minus V naught. And this gives us C1. There may be algebra errors along the way, but I do not think so. It looks okay. Now, where did I use the uniqueness theorem? It seems like I have done everything perfectly reasonably. I had enough equations, enough unknowns, I solved them. Well, the uniqueness theorem comes in my ability to look at a problem where I said I have a ground plane, I have epsilon 2, and I do not know what I have here. And I am able to say, okay, I know that at this point I have a potential, or I will say I know what the normal component of the flux is. By specifying one or the other of these conditions, I have uniqueness here. Once I have uniqueness here, there is only one solution possible here, which means that if I specify phi in here is completely known, which means in turn dn is completely known. So at this midpoint, if I assume phi, I have solved the lower region, I have got normal derivative. But in the upper region, if I have got normal derivative, I know phi, I can obtain phi again. This allows me to build up an equation that allows me to pin down what phi is at the midpoint, and therefore what the solution is everywhere. This approach, which looks very cumbersome, is extremely powerful. In fact, this is how most problems in Poisson involving Poisson's equation are solved. So you will have to get used to this kind of problem, and I am sure you will encounter many more complicated versions of this problem. Now, the method of images can be used in somewhat more complex situations. Supposing I have two ground planes which are at 90 degrees and I have a charge q. If I have a charge q here, I can put a charge minus q here, and these two charges together will make this entire plane grounded. Now, for this charge, if I put a charge minus q here, then this entire plane will become phi equals 0. But if I put this charge here, that upsets this boundary condition. If I put this charge here, that upsets this boundary condition. So what I would like to do is I would like to put an image charge for this charge also. And luckily, it turns out that this is not only the image charge of this, but it is also the image charge of this charge. So, now if we have all these 4 charges in place, this pair of charges as well as this pair of charges enforce phi equals 0 on the horizontal wall. This pair of charges as well as this pair enforce phi equals 0 on the vertical wall. So, this set of 4 charges achieve ground on both of these plates, and I have not introduced any charge in the main chamber, and therefore, by uniqueness I have got the correct solution. So, the electric field is again equal to q over 4 pi epsilon naught sum on I equals 1 to 4. Well, I will keep the q inside, q I over r minus r I cube times r minus r I. It is exactly the same as the ground plane, except now I have additional charges. Now, note the important extra charge I have added. I have added an extra charge here which was not required by this charge, but was required by these 2 charges. But it does not matter, as long as the charge I add is not going to fall inside this region, it is a perfectly acceptable problem, and this has given me an answer. Now, we can try to do the same problem for a geometry like this. Let us say this is 30 degrees. So, it is 120 degrees. Now, I put a charge here q, I get a charge minus q here. That makes this plate grounded. Now, I put a charge here which is minus q to make this plate grounded. I will now want to put a charge reflected against this line, so that this charge will also be giving me ground, and similarly there will be a charge here. Unfortunately, when I do this, I end up with one more charge here, and this is not acceptable. After I have done all these reflections, I am getting a charge which is inside the region of interest, and the moment that happens, the moment I have a charge that is sitting inside my region of interest, this whole method fails. Method of images can't be used. Method of images is based on the idea that we can add image charges beneath the plates, and if the image of an image ends up being above the plate, then this method automatically fails. Luckily for us, there are other methods that solve this particular problem, and so we are not really limited by the fact that we couldn't solve it. But you must keep this in mind. The method of images gives you some very simple answers, but there are lots of times when it does not give you a simple answer, and in that case you have to go to other methods. Now, let us go back to Laplace's equation and Poisson's equation. I want to go back to one simple problem which needs to be properly understood. So, again this one dimensional capacitor, again I have a dielectric constant epsilon, but now I am going to add a conductivity. Any real capacitor is filled with real material, that real material has a little bit of leakage. If I apply a voltage 1 volt across that dielectric, the current through it is not 0. It may take a year to discharge, but still there is a tiny bit of current that is leaking through this material. So, there is a small amount of sigma. Now, the question is, we found a solution using Poisson's equation, but in the presence of sigma, does this solution work or does it fail? So, let us work out the answers. First of all, we have del squared phi equals minus rho over epsilon. This is true, but we do not know rho. If there is leakage, it is possible that charge collects here and there. On the other hand, we know that if we have conductivity, we have that current is equal to sigma Jx is equal to sigma Ex. X is this direction, x equals 0 is here, x equals t is there. And since Ex is given by phi, it is equal to minus sigma d phi dx. Now, Jx itself is flowing, well, if I put a voltage V naught and ground it, current will be flowing downwards. Now, this Jx itself satisfies another law, which is if I draw a cylinder, the amount of current entering, I entering, is equal to Jx times dA, the area. The current leaving is equal to, so I will call this Jx1, Jx2 dA. Now, if the current entering and the current leaving are not equal, it means charge is slowly accumulating, but that cannot happen in a DC problem, and therefore, I must have Jx is equal to constant. More generally, the equation I should have is divergence of J is equal to minus del rho del t. I believe I derived this earlier. So, this is saying the same thing, divergence of J, which is djx dx is equal to 0, or Jx is constant. So, what does that say? It says minus sigma d phi dx equals constant. If I take the derivative again, that tells me d dx of minus sigma d phi dx equals 0. We can assume sigma is constant. So, we get a second equation. This was one equation. The second equation we get is del squared phi equals 0. So, there is one equation coming out of Poisson's equation, one equation coming out of current. Now, as it turns out, these are not independent equations. They can both be true if charge density were 0. And so, in this particular problem, what we are concluding is this equation is true and rho is equal to 0. So, the way to look at this problem is, I apply a voltage V naught, 1 volt maybe, a current starts up. So, constant current is flowing through. Because constant current is flowing through, no charge needs to build up. Because no charge needs to build up, the region of dielectric is charge free, and we end up solving Laplace's equation anyway. Now, all this would fail if maybe the sigma of the system is not constant. Maybe it is equal to sigma naught times 1 plus x over d. That is, the conductivity is weak here, conductivity is strong here. If we had such a system, then what would happen is, this would still be true. Poisson's equation is perfectly valid. This would be true, J equals sigma E is true, and E is derived from potential, so that is correct. J x being constant, well, that follows because of DC conditions, which means minus sigma d phi dx is constant. That is also correct, which means time rate of, space rate of change of this quantity is 0. So, up to this point the equation is correct. The problem now is sigma is not constant, it is a function of x. So, when you try to write this equation out, that equation will not be true. Instead, that equation becomes divergence of sigma grad phi equals 0. So, instead of del squared phi equals minus rho over epsilon, now you got divergence of sigma grad phi equals 0. This problem can be worked out, it is not very difficult. Let me write it out. It is d dx of sigma naught times 1 plus x over d times d phi dx is equal to 0. So, this d dx either acts on d phi dx or it acts on x over d. So, you get two terms, sigma naught times 1 plus x over d d phi dx plus sigma naught d dx of x over d d phi dx equals 0. So, you can see that there is a new term that has come in, which complicates the equation. Luckily, we can directly solve this problem. Since this is equal to 0, it must be true that the bracket quantity is constant. So, we can write this as sigma naught 1 plus x over d d phi dx equals constant C1, which means d phi dx is equal to C1 over sigma naught 1 plus x over d, which again means we can integrate this to get phi is equal to C2 plus integral to x C1 over sigma naught 1 plus x over d dx. Once again, the answer is in terms of two unknown constants, and we have two pieces of information. We know that phi at 0 is equal to 0, phi at d equals v naught. So, using these two pieces of information, we can determine C1 and C2. Now, what does this tell us? We can do the algebra. What it tells us is that if you have certain kinds of capacitors where you have leakage charge, and if the properties of the material are not uniform, you can actually have a solution that does not satisfy del squared phi equals 0. Instead, it satisfies something else, and that something else means that there is a space charge, a charge of electrons building up inside the dielectric. So, the dielectric actually becomes charged, and over time that charge settles in every part of the dielectric to make sure that this equation is true. This is the equation that controls a leaky capacitor, because we cannot have current building up, that is not acceptable. But while it is building up, it is possible to have del rho del t being non-zero, because charge is building up. Once it has finished building up, it must be true that J is constant, and if J is constant, it must be this equation that is true, and therefore there is charge present.